Picture a traditional data center, a fortress of steel server racks locked behind concrete walls and biometric scanners. Now, shatter it. When an organization migrates to the cloud, that physical perimeter disappears. You are trading concrete walls for lines of code, replacing physical air gaps with purely logical isolation. The standard security principles still apply. You still need to defend the confidentiality, integrity, and availability of your data against standard network attacks. But the distributed architecture hosting that data introduces a unique class of vulnerabilities. This is the central trade-off of cloud computing. You surrender direct ownership and control of the physical hardware. In exchange, you must rely on the service provider to manage the underlying infrastructure and enforce software-defined boundaries. Because the physical hardware is no longer yours to protect, trying to secure a cloud environment by simply building a better network firewall is a structural guarantee of failure. To understand exactly where these new vulnerabilities live, we have to look at the baseline architecture of the cloud, the shared stack. In a traditional on-premise setup, a bare metal server is dedicated entirely to your organization. The application layer sits directly on top of the physical hardware, completely isolated from the outside world. But in the cloud, a new software component called a hypervisor, or virtual machine manager, is injected between the hardware and the applications. This layer allows a single physical server to host multiple distinct virtual machines simultaneously. This thin software layer is now the only barrier preventing Company A from accessing Company B's database. It is a logical partition, replacing what used to be a physical air gap. The security of every single cloud tenant is tethered to the integrity of this single shared virtualization layer. This image highlights a core concept known as multi-tenancy. Multi-tenancy is the practice of multiplexing virtual machines from entirely disjointed, unrelated customers upon the exact same physical hardware. This creates a unique co-tenancy risk. An attacker doesn't need to breach your corporate network from the outside. They can simply rent a virtual machine on the exact same physical server rack that hosts your sensitive data. An attacker can execute side-channel attacks by monitoring shared physical resources, like CPU heat fluctuations, to infer a target virtual machine's data. A more severe scenario is a hypervisor escape, where malicious code breaks out and infects the foundational virtual machine manager. This slide details how a compromised hypervisor allows an attacker to bypass access controls, interacting directly with any hosted virtual machine. Furthermore, the To Types section shows that virtualization architecture choices, full versus para-virtualization, shift exactly where these vulnerabilities are located. Because of this shared architecture, resource isolation is the primary defense keeping data secure. But software-defined isolation is inherently fragile compared to physical separation. In a multi-tenant environment, your most dangerous adversary might operate legally on the exact same microchip. Beyond the hardware layer, the cloud introduces a completely new temporal challenge: elastic scalability. Depending on demand, compute resources can rapidly multiply into massive server clusters and then delete themselves just as quickly when the traffic subsides. This elasticity creates a continuously moving target. Static IP tracking and traditional security auditing are useless when the servers themselves only exist for a few minutes at a time. With physical borders gone and IP addresses constantly shifting, Identity and Access Management, or IAM, becomes the new absolute perimeter. IAM is a framework of policies and technologies that ensures only authorized users and services can access specific cloud resources. In a traditional breach, an attacker might slowly exfiltrate a database over several weeks. A compromised cloud account holds the API keys to the infrastructure, granting attackers administrative power to instantly wipe every server cluster from existence. Securing this requires enforcing the principle of least privilege, giving users and scripts only the exact permissions they need, across thousands of ephemeral virtual machines spinning up and down every hour. When your entire infrastructure is generated and managed by code, user identity management becomes the ultimate single point of failure. This brings us to a paradox at the core of cloud computing: the loss of control. Organizations entrust their most sensitive data to infrastructure they cannot see, they cannot configure, or physically locate. This creates a vast trust deficit between a client's strict security requirements and the opaque operational reality of a third-party data center. Gartner's 7 Security Risks framework categorizes the threats of provider opacity. Clients cannot verify privileged user access or data segregation. Forensic hardware audits for investigative support are impossible in shared environments. And shifting data location instantly creates regulatory compliance violations without the client knowing. The only operational mechanisms bridging this massive loss of control are surface-level agreements. Surface-level agreements, or SLAs, are legally binding contracts that mandate the exact performance, security, and uptime standards the provider is required to maintain. Because you cannot verify the hardware yourself, engineering secure cloud systems requires treating the underlying physical infrastructure as a completely untrusted, hostile black box. If the infrastructure itself cannot be implicitly trusted, we have to look at how the data survives as it moves through it. Data exists in a continuous, vulnerable loop known as the data lifecycle. During the processing and transmission phases, data is exposed to severe application layer vulnerabilities. Attackers can manipulate web services and intercept data while it's in motion. This slide details the specific confidentiality questions surrounding the deletion phase. When a client deletes a file, how can they guarantee the data is truly wiped when the cloud provider controls the underlying physical drives and automated backup servers? This threat model expands exponentially in inter-cloud environments, where an application relies on microservices distributed across multiple different cloud providers, like passing data from AWS directly to Microsoft Azure. The API pipelines connecting these distinct clouds create massive new attack surfaces. They often route traffic outside the internal security boundaries of any single provider, exposing the data to interception. A multi-cloud architecture automatically inherits the weakest security link of any third-party service attached to it. Because the infrastructure it traverses cannot be guaranteed secure, the data itself must carry its own strict cryptographic security policy at all times. The cloud threat landscape is a complex web of shared hypervisors, shifting logical boundaries, and opaque provider operations. Traditional security focused on building thicker concrete walls. Cloud security requires managing layers of logical abstraction. Defending against multi-tenant risks requires absolute hypervisor integrity and vigilant software-defined resource isolation. Managing the chaos of elastic, dynamically scaling instances demands flawless, automated identity and access management policies, and navigating provider opacity requires a rigorous understanding of the Gartner framework and aggressive enforcement of service-level agreements. This is the architecture of trust. In the cloud, trust is never assumed by default. It must be procedurally, legally, and mathematically engineered into the system from the ground up. Now that we understand the architectural vulnerabilities of the shared stack, our next step is to examine the specific cryptographic mechanisms used to mathematically enforce that trust. In the cloud, you are merely renting the computer, but you, and you alone, own the ultimate responsibility for its security.